Take this dark, jagged piece of material and press it against a solid block of ice. It slides right through it like butter. You might think that's happening because the edge is incredibly sharp, or maybe it's super heavy, but it's actually doing something much stranger. It is rapidly stealing the heat right out of my hand and dumping that heat directly into the ice. The speed at which a material can move heat is called its thermal conductivity. This chart compares everyday metals used specifically because they are great at moving heat. Copper is here. Aluminum is here. But the material cutting the ice is all the way up here. It dwarfs the metals we usually rely on. This is a polycrystalline diamond, a cluster of millions of microscopic diamond shards bonded together. Its heat-stealing property is exactly what the modern technological world is desperate for. To understand why, we have to look at the tiny on-off switches that run almost all modern computers, silicon transistors. This is one of the earliest prototypes. It's massive, crude, and easy to see with the naked eye. This chart plots the physical size of those transistors over time. For decades, engineers have consistently shrunk them down, doubling the number they can fit onto a computer chip roughly every 2 years. We pushed this engineering so far that today's transistors are smaller than a red blood cell. In fact, they're roughly the size of a flu virus. Physics won't let us make these switches much smaller without losing control of them. So instead of packing more transistors side by side like single-family homes, engineers are now stacking them vertically, like multi-story apartment buildings. But when you pack billions of microscopic switches on top of each other and run electricity through them, they generate an enormous amount of heat. And in a 3D stack, that heat has nowhere to go. Computers rely on copper and aluminum heat sinks to pull that thermal energy away. When those metals can't keep up, the heat gets trapped. The chip is forced to slow down, run less efficiently, and if it gets too hot, it physically breaks down. Whether we are training advanced AI models or running complex simulations for deep space missions, the math requires more computing power. But right now, we are hitting a literal thermal wall. To keep progressing, we have to find a material that can move heat much, much faster. That brings us back to those dark diamonds. Researchers realized that if they could wrap these overheating computer chips in a diamond blanket, they could siphon the trapped heat away almost instantly. You can't just mine these out of the ground. Digging up millions of carats of natural diamonds is incredibly expensive. But more importantly, natural diamonds take millions of years to form deep inside the Earth's mantle. During that time, they trap little pieces of other elements inside their crystal structure. Those microscopic impurities actively block the flow of heat. To build a functional cooling blanket for a computer, material scientists needed a diamond that is structurally purer than anything nature can create on its own. After World War II, the United States military and aviation industries needed millions of carats of diamonds every year just to cut, drill, and grind parts for airplanes and armor. To meet that massive industrial demand, researchers tried to build their own. They built giant mechanical presses that mimicked the extreme weight and heat of the Earth's crust, literally squishing carbon together until it crystallized. That brute force, high-pressure method worked, but today they use an entirely different, far more elegant process called chemical vapor deposition. It works a bit like a high-tech oven. They place a tiny diamond seed inside a vacuum chamber, pump out all the air, and fill it with a very specific mixture of hydrogen and methane gas. Then they ignite it by blasting those gases with microwaves 10 times more powerful than the one in your kitchen. This supercharges the molecules, creating a volatile cloud of glowing green plasma. Inside that intense plasma storm, the energy rips the methane molecules apart. The pure carbon atoms separate from the hydrogen and literally snow downward, bonding to the seed layer by layer. By strictly controlling those gases over several weeks, scientists grow those dark polycrystalline diamonds we saw earlier. They have no jewelry store romance, but they are highly engineered thermal superconductors built entirely for data centers. When engineers take synthetic diamond blankets and apply them directly to densely stacked computer chips, the physical limits of the hardware shift immediately. In recent experiments at a data center in San Francisco, researchers swapped out standard cooling hardware for diamond. The operating temperatures of their high-powered graphics processors plummeted. This chart maps the performance of those two setups. The standard chip hits a thermal ceiling right here and stops scaling. But by moving heat away faster, the test doubled the computing output of a single server. If these tests scale, it means we can increase the density of our digital infrastructure. Instead of needing 2 massive data centers to meet growing demand, we could squeeze that same power into a single facility. We are past the point of theoretical research. These synthetic diamond components are actively running inside high-end servers right now, directly bypassing the physical limits of standard silicon. That same thermal efficiency solves hardware problems all the way up in orbit. Right now, satellites require huge, bulky radiator panels to manage the heat generated by internal electronics, wasting massive amounts of physical volume and weight. By integrating diamond cooling directly into the satellite circuitry, aerospace engineers can shrink the overall size of the heat management hardware, leaving far more room for scientific instruments and larger payloads. And moving extreme heat is just the first application. Researchers are finding that these pure synthetic crystals can withstand massive doses of space radiation and handle the intensely high voltages required for next-generation electric vehicles. By mastering the extreme forces of the Earth's core inside a vacuum chamber, we've taken a material once used for status symbols and made it a thermal tool that can push our computers past their physical limits.